So let's put that derivation to use in a calculation. And what we want to do is determine the electric field strength at a point 0, 5, 5 from an infinite line of charge with charge density of 5 nanocoulombs per meter. And the line of charge is located at the point y equals 4 and z equals 0. So let's just draw that situation first. We've got our Cartesian coordinate system, and we've got a point that is 0 in the x-axis, it is 5 in the y-axis, 1, 2, 3, 4, 5, and it is 5 in the z-axis, 1, 2, 3, 4, 5. So that point is, about right there, 0, 5, 5. And the line charge is located at y equals 4 and z equals 0, so that's 1, 2, 3, 4. Right there, nothing in the z. And why didn't we specify an x-axis? Well, it's because it's a line charge, right? It is, by just giving the y and the z coordinates, we've specified the fact that it lies along the x-axis in this case. And this has a linear charge density of 5 nanocoulombs per meter. So we've got the z-axis, the x-axis, and the y-axis there. The first step to solving this problem is that we need to isolate the axis to the ones that correspond to the rho and the z-axis in the cylindrical coordinate system. That can sometimes be a little bit confusing, and what you need to kind of look at is that, well, the infinite line charge here is oriented along the x-axis. That means the cylinder that we're looking at is going to be oriented in kind of this direction right here. So the cylindrical coordinate system that we're interested in is going to be oriented along the x-axis here. And so if we were to translate that into the two dimensions that we're interested in, we have the z-axis, which is going to be this direction here, and then we're interested in the rho axis, which is kind of the separation between this point and this point right here. So, the z-axis and the y-axis, z and y. So if we were to look at that, because remember, we don't care about the effects along the length of it, because that's the path that we integrated along. So we don't care about the x-axis in this case. We just care about the z and the y. So if we just simplify these points down to the z and the y, p becomes 5, 5, and the line charge stays at 4, 0. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That's point P right there, and then this line charge is at the point 4, 0. 1, 2, 3, 4, 0. So the vector that points from normal to the line charge to the point is just that vector right there. And you can kind of picture that rho L is pointing out of the screen and into the screen from there. So the first thing we need to do is we need to determine what the vector pointing from the infinite line charge to the point in space is. And that is, the vector in cylindrical coordinate systems is rho a hat rho, right? The length of this vector is rho, and it's pointing in the a hat rho direction. Well, for us, if we want to translate that to the z-y plane, it is equal to 5 minus 4 a hat y and 5 minus 0 a hat z. So that's equal to this vector right here, but I've just written it in rectangular coordinates. So that's just a hat y plus 5 a hat z. So rho a hat rho is equal to a hat y plus 5 a hat z. The magnitude of rho is therefore equal to 1 squared plus 5 squared is just equal to the square root of 26, and the unit vector pointing in the rho direction is just going to be a hat y over root 26 plus 5 over root 26 a hat z. I can now take the results of the calculations I did previously, and I've got the calculus that I did previously. E is equal to the linear charge density divided by 2 pi epsilon 0 times rho squared, and that points in the a hat rho direction. So in the problem statement, we were given a linear charge density of 5 times 10 to the minus 19th coulombs per meter. We've got 2 pi 8.854 times 10 to the minus 12th farads per meter. Oh, we've got the magnitude of, sorry, that's the magnitude of rho squared. The magnitude of rho squared is just the square root of 26 squared. Now we need to multiply that by the unit vector pointing in the rho direction, which is a hat y over root 26 plus 5 over root 26 a hat z. And we multiply all this out, and you get that the electric field intensity at the point P is equal to 3.46 pointing in the y direction plus 17.28 pointing in the z direction. And since it's an electric field intensity, it's in units of volts per meter.